Good evening, madam. Mallika, madam.
Good evening, sir.
Good evening. Madam, within 5 minutes, we'll start, madam.
Okay, sir. Okay, sir.
Okay.
So, good evening, madam. So, I would like to introduce madam to all the participants. So, Dr. Mallika, madam, is a professor and dean IQAC from the Department of Civil Engineering at VNR Vignana Jyothi of Engineering and Technology, with 23 years of teaching experience and 6 years in structural design and consultancies. She specializes in finite element analysis, earthquake engineering, optimization techniques, and structural health monitoring using artificial intelligence. Madam has guided numerous UG, PG, and PhD projects, published extensively in peer reviewed journals, and organized several national and international conferences. She is actively involved in curriculum development and holds memberships in academic boards. She has received multiple awards, including gold medals from academic excellence and recognitions from her contributions to health, structural engineering, education, and research. Madam is also a licensed professional structural engineer and serves on editorial boards of reputed journals. Now I introduce Mallika Madam to your valuable presentation.
Thank you, sir. Thank you very much for the nice introduction, sir. So, can I start, sir?
Yes, ma'am.
I'll share my screen. Is my screen visible, sir?
Yes, ma'am.
Yes, sir. So good evening, everyone. Good evening to all the participants in the ATL FTP, which is on the role of Industry 4.0 in civil engineering for future construction. Today, my session will be focusing, which will be starting with some fundamentals and taking a research example also, the structural health monitoring using deep learning techniques. So the contents of my presentation are as follows. We will be giving an introduction to structural health monitoring, what it is, and what are the methods of structural health monitoring, why we need to go for artificial intelligence and machine learning techniques in SHM, and what is the role of deep learning in structural health monitoring. And the deep learning model, that is convolution neural networks, we will be learning a little bit about this, and then with a research example. So what is structural health monitoring system? Majority of us might be knowing what it is, the process of implementing a damage detection and characterization strategy for engineering structures. This is a classical definition of structural health monitoring system. As you can see from the figure, so if you take an example of a structure which is to be monitored, lots of sensors will be placed embedded or surface bonded to the structure. So we'll be receiving data from these sensors through the data acquisition system, and the data will be processed through the processing units, and through the algorithm what we are writing based on different platforms, we will be detecting the damage, whatever is the form of damage. So sometimes we detect the damage, sometimes we try to predict the damage also through the algorithms like AI-based machine learning algorithms and all. And also we are able to find out whether the damage is localized or globally, whether it is present within the structure. So to implement this one, we require lots of support systems like hardware components and software components, etc. So participants and all, we need to understand the difference between structural health monitoring system and condition assessment of a structure. Generally, we do condition assessment in civil engineering infrastructure, like doing that once in a while. That is condition of the structure, assessing the condition of the structure at that moment of time. But whereas the name monitoring says it is a continuous monitoring system from a structure, which is possible only with the help of some sensor technologies. So generally the concepts of structural health monitoring system, as we can see from this slide. So the structure is the basic thing, the hosting part, in which we are trying to identify some sort of damage if it is present in the structure through the sensors, as I said just now, whether it is embedded within the structural system or surface bonded, and then data is acquired and the transferred and stored. Lots of big data we will be dealing with, and the data has to be managed through different sorts of algorithm. That is, analysis is done and the diagnosis, and the next stage will be prognosis, of course. So to predict how much is the residual life of the structure. This is how the entire structural health monitoring system, whether it is in the form of condition assessment or through a continuous monitoring mechanism. So to understand this, first we need to understand what a damage is. A damage is an intentional or unintentional change in the material or in the geometric properties or in the boundary conditions or in the system connectivity. So as we define the structure as assembly of members which are connected by either rigid or flexible joints, which are capable of carrying the loads and transfer the loads. This is how we define a structure. So if there are any changes in the even connectivity also, whether it is a rigid or a flexible joint also, that is called as a damage. So entirely any change in these kind of events which adversely affect the current performance or future performance of the systems is known as a damage. So as a structural engineer, it is our duty, or a civil engineer, it is our responsibility to find whether a damage is present in the structure, or any incipient damages are also going to happen in the structure or structural component. So as I said, damages are due to poor construction practices, maybe lack of quality control, or extreme temperature stresses, or lack of maintenance or monitoring, like damages such as surface cracks, segregations, settlements, degradation before their design life due to environmental exposure. Sometimes extreme environmental exposures also cause some sort of degradation, whether it is RC structure or steel structure or any different kinds of materials also. And sometimes due to unforeseen loads also, the damages are going to happen within the structures. As you can see in the figures here, you can see extensive cracks may or may not be structural cracks, or some sort of corrosion, or some sort of joint connectivity problems like loosening of the bolt system, and if it is a welded joint, then rigidity, extreme rigidity, which is causing the welded joint to fail. Such sort of damages are going to happen in the structures. So we need to identify the damage. What are the different identification levels of the damage? So localization, after identifying, we need to do the localization. Broadly, we can say one side is diagnosis, another side is prognosis. So diagnosing the damage is identifying the damage and its location. Prognosis is classify the damage so that you can do later on what are the required prognosis need to be carried out for the structure, the repairs, rehabilitations, and then assess what is the extent of damage and predict the residual life of the structure. So this process of damage diagnosis is decomposed into 3 levels. That is early damage detection and localization of the damage, and quantify the damage. The extent of damage can be quantified. So the first level is global strategy, that is early damage detection, aiming at evaluating whether the damage has occurred throughout the structure. So that means first thing is we will be identifying whether there is damage in the system or not. Then we will focus on the localization of the damage. The second and third levels are local strategies. So level 2, that is damage localization, is intended to identify where the damage is in the system, the location of damage. So how we engineers and scientists study damage? The existence of damage, the
Madam,
location of
excuse
the
me, this is Madam. Sorry for the
Sir.
intervention. This is
Sir.
Dr. Chandrasekhar, HOD. Madam,
Yes,
will you check for once the slide? As far as my concern, the slides are not changing, madam.
1 second, sir. I'll just check.
Now it is okay, madam. They are coming.
Okay, sir. Thank you, sir.
Okay, madam. Right.
Now, sir, you are able to see this slide, sir, damage definition.
Yes, madam. Yes, madam.
Hopefully the change of slides is seen, sir. Hello?
Yes, ma'am.
Yes,
Slides
madam.
are changing.
Yes, sir.
Now
Yeah.
the damage definition. Okay, right.
Yes, sir. Yes, sir. So we are focusing on how engineers study the damage. So whether the damage exists in the system, where the damage is occurring, the location, what kind of damage is present, type of damage, whether the damage is due to flexure or due to failure in the joints or due to any shear failure. So the type of damage present in the system and how severe the damage is, the extent of damage, how much useful life is going to remain. That is the prognosis part. So local versus global damage detection is very, very important. Not all the methods we follow for damage detection. So they are not going to focus on the localization of the damage. this is where we need to understand the limitations of damage detection methods with our conventional mechanisms. So then what should we do to identify the damages? So in the structural health monitoring, what we understand is there are two kinds of broad categories of identifying the damage. The first one is non-destructive in situ structural evaluation, what we generally 80% of the times we are going to follow. And the second one is using several type of sensors, whether it is temperature sensor, deflection sensors, stress sensors, or whatever is the type of sensor, which are embedded or surface bonded to a structure.
Madam, excuse me, your slides are not rolling, madam. Again, it is stuck on at the damage definition.
Now, sir?
No, yes, one by, when you change it, then now it is rolling.
In the slide mode, I think they are not seen, sir.
Okay.
In the presentation mode, I think there is a problem. Now you are able to see, sir?
Yes,
Yes,
madam.
ma'am.
I think problem is when I'm going to the presentation mode, they are not seen, sir.
Maybe the problem.
Once again, I'll just try, sir.
Okay.
Let's try with attached screen.
That's what I'm doing, sir. 1 second, sir. Now, sir?
Okay, madam. Now it is okay.
Previous one, sir? I've changed the slide. You are able to see?
Yes, ma'am.
Yeah. Thank you. So the structural monitoring, health monitoring systems, what we generally follow is using conventional methods and then using some data-driven kind of techniques. So the non-destructive in situ structural evaluation methods are generally based on physics-based approaches, as we all of us know, that is wave propagations. And the second one is data-driven approaches. The physics-based approaches, the conventional methods, they establish correlations between measurable physical parameters and structural conditions like any deflections, stresses, and microstructural changes. And the data-driven approaches rely on sensor-generated data and computational models to assess the health of the structure, to detect the anomalies and predict the future performances. So this is where the difference between NDTs, what we generally follow, and the latest techniques which are based on the data-driven approaches, that is data from the sensors. So entire goal will revolve around structural safety, strength, integrity, and performance of the structure. So our aim and our title for today is going to revolve around the data-driven approaches. So based on the sensor type of data. But here, when we are going to use deep learning techniques, we are going to rely on the imagery data from a structure, because there are various limitations even for the sensor data and the sensor operations also. So if you see this slide, sir, you are able to see the slide, sir?
Yes, ma'am.
Yeah. So it is generally the structural health is analogous to human health. So whenever we get some problem, health issue, the medical doctor is going to monitor patient's health. Like when we cross 50s, we generally go for different kinds of tests on a regular basis, and then we try to diagnose with any kind of chronic diseases with the help of some medical equipment to check the overall health, and then corrective medicines will be followed to maintain our human body. Similarly, for the structural health monitoring engineer we, the civil engineers or structural engineers, we try to assess the condition of the structures. That is through the sensors to check the overall health of the structure. If excessive stresses, excessive deformations are existing in the structure, then we correct those kind of conditions by means of some kind of retrofitting measures, some repair and rehabilitation techniques. So this is analogous to human health. So we need to take care of our structural health also. So this is the crucial factors which determine the effective strategies which need to be followed for health monitoring of the structure is depending on whether that is based on like the inspection scale. Sometimes if we want to monitor the health of a bridge, it is a huge structure, very long structures. So then we need to now choose the methodology of SHM based on whether you need to go for global or local. The type of response, whether it is a static, subjected to static loads or dynamic loads like winds or earthquakes. Like based on the behavior of the structure, like linear or non-linear basis, based on the computational models, model-based or signal-based, based on the feedback from the structure, active or passive modes, based on the excitation. Sometimes we need to go for other than free vibrations, we need to induce the forced vibrations or ambient excitation to the structure, get the responses, and then we need to decide on the effective strategies. And sometimes based on the capturing of the data domain, that is time domain or frequency or both. Because whenever we are using some PZT sensors, you are going to get frequency domain. But if you are using any accelerometers, you get the data on time domain basis. You need to convert that into frequency domain using FFT, Fourier transforms, and also based on the solution, forward or inverse methods. So based on what is the type of strategy we need to follow, you have to determine the effective methodology for SHM. So based on that, again, the structural assessment methods, response-based techniques, reliability-based techniques, acoustic emission techniques, feature extraction methods, computer vision methods, machine learning in data-driven methods. The last two are the ones what we are going to focus in today's session. So once again, the structure and the human body. So here we need to understand brain as the interpretation unit. So same thing, we are going to take help of one of the deep learning techniques, which is going to mimic the brain's functions. So here nerves are represented by transmission unit because we have the neurons, which are nothing but they are going to carry the data. They are called as nerves or neurons. So same thing we are going to understand in the coming CNN methodologies. So three things we need to understand: test structures, sensors, so how we interrogate the data and interpret the data. So for smart sensing in the structural health monitoring, the moment we say smart, there will not be any human intervention. So the components include structures, sensors, data acquisition systems, managing the data, transferring the data, because we will be dealing with n number of sensor data, and the data is for every microsecond we will be receiving the data from each and every sensor. You can imagine so many microseconds into 10 power minus 3 of a second multiplied by 60 minutes multiplied by 24 hours in a day. So huge data we will be having from the sensors, n number of sensors. But is all the data is meaningful? Then we need to manage the data. How the data need to be transferred? We need to take help of some kind of cloud mechanisms for storage and transferring the data. And after that, whatever the data which is meaningful, which can have some meaning from the structure, which carries the data from the structure, can be interpreted for the diagnosis of the damage. So then later on, the operational evaluation will be done based on what is the life safety or economic justification for performing the SHM, and how damage is defined for the system which is being investigated, how multiple damage possibilities are there, what are the causes of concern, what are the conditions, both operational and environmental, to be monitored, and what are the limitations on acquiring the data in this environment. So all the sensing systems, what we were talking about, like transducers will be there, actuators will be there, analog to digital converters will be there, digital to analog. The moment I say sensor, so it is going to give us voltage. That is, you are going to get analog data. So directly you are not going to get deflection from a LVDT. You are going to get the voltages. That is analog signals. You need to convert that into a digital signal using A and D converters. Similarly, vice versa from digital to analog converters. So such sort of some complex systems which are going to inherently connect the data from all the sensors. So that signal conditioning need to be done. Some noise filtrations have to be done. So for all those things, you need to do some signal conditioning, and for which you require power, you require telemetry, process the data and store the data. So all are sensing systems. So there are different sensors, as I said. So you can see transducers which convert the changes in the field variables like acceleration, strains, temperature to changes in the electrical signals. That's why we receive voltages, impedances, resistances, all those things. So like this, you can see here the data acquisition systems, analysis, post-processing and all. But all these sensing systems have some limitations which pose some kind of problems in handling the data. So that's where we need AI in SHM. So why artificial intelligence? The need of AI in SHM. So we need to handle huge data from the sensors. Sensors cannot measure the damage. It only sends that particular kind of physical parameter from the structure in the form of voltage to the remote station. Feature extraction and statistical classification is also required to convert the sensor data to damage information. And damage information depends on the intelligence of the sensor feature extraction. So all these things are stressing on the need for AI in SHM. So we are, as you see from these figures, so we need to collect the data from the physical system, that is structure, through the transducer sensors, do some signal conditioning, processing, convert that analog to digital signals, and then send to the remote station. And we need to sometimes normalize the data. Whatever is the data format, original raw data cannot be fed into the computer for data analysis directly or for data predictions. So you need to normalize the data depending on the type of the data. So how to normalize the data and then clean the data? So whenever you are importing the data, sometimes you need to merge the data sets. Multimodal data also will be there. Rebuild the missing data, standardize, that is normalization, delete the duplications, verify the data. Sometimes you need to compress the data. As I said, fusion from different sensors, you need to fuse the data and extract the features. Not all the data is able to extract the features which are required to diagnose the damage. So for that one, you need to do lot of discrimination of the features, whether to go for statistical modeling or directly you need to feed whatever the features you are going to extract from the data. So the feature extraction refers to the process of discovering meaningful information from the raw vibration measurements or any kind of raw data. So features are often known as damage sensitive features. If you are collecting a vibration data, for example, then you will be having free vibrations, that is natural frequencies, and mode shapes as the damage sensitive features. Not only that, sometimes the modal energy and also damping parameters and statistical modeling of these features like natural frequencies also serve as damage sensitive features, for which we need to do some sensitivity analysis studies, which is going to give us correct damage prediction. So as you see from the slide now, so artificial intelligence it's a global intelligence techniques which uses computer science and data to enable problem solving in machines. And in machine learning, it refers to the study of computer systems that learn the data and adapt automatically from the experience without being explicitly programmed. That is what is machine learning. Machine is going to learn on its own automatically. Then
हाँ,
deep
दो
learning
time
is
पे।
again a
कहीं
subset of
कहीं अभी
machine
खाली
learning technique.
मुजफ्फरपुर में थोड़ा वर्क हो रहा है, लेकिन वो मुजफ्फरपुर में भी थोड़ा सा दिया है, नहीं तो अदरवाइज बहुत अच्छा
Sir,
है।
somebody's mic is on. Can they mute? Yeah, deep learning is a machine learning technique that layers algorithms and computing units, that is neurons, into artificial neural networks that mimic the human brain. So we can understand now artificial intelligence, a broad intelligence that uses computer science and data. For all these things like artificial intelligence, machine learning, and deep learning, they are completely based on the data. So the quality of data, what we are going to give the input into all these algorithms matters a lot, and which is going to be the output is going to be depend on the quality of data, whatever we are giving as input into these models. So machine learning, we have supervised and unsupervised learning models. Supervised is there should be a human intervention, a supervisor who has to give the instructions to the model to perform such kind of a particular operation. Unsupervised, the machine itself learns automatically from the past experiences, and then it tries to predict whatever is instructed to the system. So deep learning is going deeper and deeper into the layers of the algorithm and tries to understand and learns by itself in order to predict predict the damage of any structure. So if you see here, same thing, machine learning, pattern recognition, deep learning architectures. So in the structural health monitoring damage detection, we use machine learnings like support vector machines, artificial neural networks, all those things. There are various other kind of supervising machine learning techniques like random boost methods, trees, so many things are there, which are applicable to earthquake engineering, structural identification, predicting concrete behavior. So all these things can be done. So predicting the early strength of concrete using machine learning algorithms and all. Deep learning architectures we use majoritarily for vision-based structural health monitoring, that is based on the imagery data, that is computer vision-based data. Like human eye, computer is going to see the data in terms of images. So the deep learning, like human brain, it is going to predict what kind of damage, what is the reason of the damage, how the damage can be predicted for different kinds of damages. So there are lots of engineering applications like data-driven SHM, IoTs, computational mechanics, lot of applications in every field of structural engineering are there. So majoritarily all are based on AI techniques, that is broadly. So machine learning methods in structural health monitoring, they have become increasingly popular nowadays with the advancements in computer technology. So and handling their capability handling large data sets. These methods offer various techniques for damage detection, parameter recognition, and anomaly detection. Supervised and unsupervised learnings are two fundamental types. Beyond this, we have reinforced learning also. Supervised learning uses labeled training data to make predictions or classifications. Artificial neural networks, regressions, logistical regressions, and support vector machines are widely used techniques. So if you see the key differences between artificial intelligence, machine learning, and deep learning, AI is generalized concept encompassing human-like intelligence in the computer machines, whereas machine learning is a subset of AI focusing on the learning from the data to make predictions. And deep learning is again subset of ML, as we have seen from the previous slides, which uses deep neural networks to learn very, very complex representations of the data. So the learning approaches are going to be different. So including AI includes ML also, and machine learning utilizes data to make decisions, and deep learning utilizes deep neural networks. There will be deeper and deeper data networks which can automatically learn the hierarchical representations of the data. So coming to AI, sometimes It may not require data to predict. And machine learning requires labeling of the data or unlabeled data. But in deep learning, we require labeling of the data. Without labeling, we cannot do that one. That is the only laborious process in adopting deep learning techniques. So you need to label the data. You need to segregate the data, label them first time. Of course, there are various platforms to label the data also. We need to label the data. Unless you label the data, you cannot further process deep learning algorithms. So training complexity is they can handle deep learning algorithms can handle complex data due to multiple layers of neural networks. Performance is especially in computer vision and natural language processing, deep learning algorithms, they are going to perform much in an accurate manner. So it is what exactly deep learning is. It is composed of networks that can learn unsupervised from unlabeled, unstructured data. It aims to learn the feature representation of the input data. DL is based on deep neural networks. Deep neural networks means the input data will have more and more hidden layers which carry some information. So that can be learned by the deep learning networks. Examples of deep learning architectures are like, as I said, convolution neural networks, recurrent neural networks, autoencoders, deep belief nets, etc. So our present session is completely based on CNNs, that is convolution neural network, which is a deep learning architecture. So let us see what is the terminology which is associated with convolution neural networks. You can see the figure here. So there is a set of flowers of two varieties. One is orchid, another is rose. They are of different colors. Rose can be of red or pink or white or whatever. Orchids are also. There are only two classification of flowers here. So if you give that image of those flowers, which are labeled initially, and then fed that into our deep learning algorithm, that is convolution neural networks, the input layer will have some kind of images, the hidden layers will be there. So whatever the features, the input layers, from the input layers, the convolution layers are going to extract as feature maps that will be reduced in dimensions, and the features are extracted to represent the exact thing pixel wise that we will discuss now. And the output will be given, and the classification will be done at the end as whether what is the type of the flower, whether it is orchid or rose. It identifies. Now this is a pre-trained model. You give input of any flower, whether it is an orchid or rose. It just simply gives you the classification as if it is a rose, it is rose. If it is orchid, it is orchid. It all depends on the percentage of accuracy of your model. Suppose if your model is like 0.98 accuracy it is having, so there is a possibility of wrong prediction of 0.02%. If you feed 100 images to your algorithm, there is a possibility of 2 images being wrongly classified. So that's how the accuracies are going to be calculated. So convolution neural network is a class of deep learning. These are specialized type of neural network designed to process grid-like data structure such as images or videos. Widely used in computer vision tasks like image classification, object detection, segmentation. So it has an ability to automatically and adaptively learn spatial hierarchies of features. Image, convolution layers, pooling layers, dense layers, and then output layers. See, if we want to do condition, for example, condition assessment of a bridge. So what is going to happen? So we are going to go to the site with some manpower, with some sort of physical equipment, and then we try to fix all those transducers to the deck slab of the bridge, and we induce some kind of vibration, and we try to get the vibration response from the deck slab, and then we try to analyze that data and interpret and then do. It takes almost lot of time, expensive process, and you require lot of manpower. And accuracy is also a question mark. Suppose, okay, we are going to do that with a conventional method like that only. We don't believe on the data dependent algorithms. But if you have inaccessible points, then we will not be able to do any sort of inspection. If you have a big chimney, so we will not be able to do immediately the inspection. You require a lot of prior preparation for that one. So if the points are inaccessible where the inspection is required, in such cases, we can utilize the services of UAV, unmanned aid vehicles, that is drone systems. You can capture the imageries from the physical infrastructure and then transfer that to your remote ground station algorithm. So then apply your data driven approaches and then you can just predict what is the damage which is going to be in the structure. So that is the advantage of your convolution neural networks, which are going to be based on our imagery data. What are the main steps in the convolution neural network processing? The input layer is the first one, which takes an image as an input. Convolution layer is the one which extracts features using filters or kernels. Activation function, which introduces non-linearity for better learning, complex learnings. Pooling layer, which reduces data size while retaining the key information. Fully connected layers makes final predictions. And output layer is the one which is going to provide the classification. Suppose if you have different classification of damage. If you take an RC structure, you have cracks, you have spallings, you have corrosion of reinforcement, you have n number of damages. If you take a steel structure, there also you have rust formation, corrosion, or loosening of bolts or something like that. N number of classes will be present, damage classes. So you can classify the output. So what kind of damage it is. So there are lots of advantages of convolution neural networks. They are very good at detecting patterns and features in the images, videos, and even audio signals also. They are very robust to translate rotation and scaling invariances. End-to-end training, no manual intervention is required. They can handle very large amounts of data for high accuracy. So there are, of course, any method you take, there will be some disadvantages or limitations. Hence, CNNs also has such kind of limitations. They are very expensive computationally. You require very, very high-end GPUs, graphical processing units are required. Very high RAMs are required to train and predict the data. So it can be more prone to overfitting if not enough data or proper regularization techniques are applied on the data. So sometimes overfitting of the data is going to happen if your sample size is very small. To avoid that one, we will be doing some augmentation techniques on the data also. And then we require to label large amounts of data initially. And interpretability is also limited. Those are the limitations of CNN. So we will be going with one small example of how CNN is going to perform operations on an image. So convolution layer is known as heart of the CNN. So every image is considered as matrix of pixel. If you take an image, pixel is picture element. What is a picture element? It is a dot in an image. So imagine if you have a picture, every picture will have some resolution. All of us will be taking lots of pictures in our mobiles through the cameras and all. Sometimes we feel resolution is not good. What do you mean by that resolution? It is a matrix of pixels in a given image. What do you mean by pixel? Picture element, it is a dot. How many dots are there in the image? Based on that, the clarity of your image is going to be. So then taking that image, which is a matrix of pixels, we will be applying some sort of filters to extract the patterns. What kind of patterns the image is going to have, whether it has sharp edges, whether it is a shape or a texture or a curve or like that, some kind of patterns we will be trying to extract through the kernels. What is a kernel? It is a filter which is applied on the image. So this uses small matrices to scan the input image. So when you will be scanning some kind of like a medical doctor will be scanning a particular organ in a body. So only that particular organ like heart, it scans from the left end to right end, from the front end to back end through your MRIs. your computer tomographies, it is going to scan and give all the details. Similarly, here also, your kernel is going to scan, usually expressed as a matrix like 3 by 3 by 3 or 5 by 5 by 3 or 7 by 7 by 3, depends on the size of your image. So this is going to help us to detect the pattern across different regions of your image. The spatial size of the filter is a design choice, but generally 3 by 3 is utilized to have good feature extraction. So the output, as I was mentioning, it is called as feature map. The kernel or filter, what we are going to apply, there are various kinds of kernels based on the application. Some kernels are meant for edge detection. Some kind of kernels are used to monitor whether the image is blur or smooth at certain pixel points, the sharpness of the image, the embossing part of the image. So like this, you are able to see from the screen, there are various kinds of kernels or filters that can be applied, and the sizes also. How to choose this kernel? So that is based on the use case, what we are going to, the application part, what we are going to apply our CNN model. So second part of CNN is introducing an activation function. There are various activation functions through which we are going to introduce a nonlinearity into our CNN network. So what is that nonlinearity? Generally, all the figures will be having only linear functions. That is simple edges it is going to identify. But if we go deeper and deeper into the layers of our deep learning algorithm or architecture, you will be learning only, because we are performing the operations through a dot matrix operations. So we are going to get only linear kind of features only. If the features are complex like curves or bends or sharpness is there, noise is there, the model will not be able to learn all those things. To introduce non-linearity so that your model can learn complex features of the image also, it is always advisable, and your deep learning architecture, that is CNN, is going to have one of the function as activation function. Generally, we use rectified linear unit, RELU, as the activation function in the CNN. So it makes the network efficient in handling very, very complex patterns also. So before applying this one, we need to understand what is stride, what is padding. As the literal meaning of stride is like, it is a step. It is a step. It determines how many pixels the kernel shifts or takes the step over the input image at a time. Like stride of 1 means the dot product is performed on n by n window of the 2D input. So it shifts the kernel by 1 pixel. The operation is carried out for the next one stride 1. So like this, you are going to decrease the stride length, results in learning more features. Suppose if I want to give my stride as 2, it skips 2 pixels and then starts its dot matrix operations. So to have more features to be learned by your algorithm, always have your stride length as 1. But it takes more computational time. So as I said, increasing the stride results in the reduced output layer dimensions and increases the computational time. Padding is the one, again, as the name indicates. So to protect the boundary data, extra pixels are added around your input image. Like it is like a border. Border information will not be lost by adding a padding. So you can have 0 padding, you can have 2 pixel padding or something like that. You can add to determine the output spatial size of the feature map. And then comes pooling layer. It reduces the dimension of your feature map while retaining the important information. There are 2 kinds of pooling which we are going to apply. One is maximum pooling, another is average. It takes the maximum value from a region, preserving the sharp features. Average pooling is going to take the mean of all the data for smooth feature extraction. You will be understanding this if we take one image example, and then we can proceed with this. So now, if you see one image, so the left side one, hopefully you are able to see my cursor. You are able to see my cursor on the screen? Hello, sir.
No, ma'am.
Okay. So the left side matrix you are able to see 5 by 5.
Yes, ma'am.
Yeah, this 5 by 5 matrix is nothing but a matrix of pixel of an image. This is an image. So which is represented by only 5 by 5 pixels. Actually, your image will be having 2257 by 257 by 5 or 2092 by 2092 pixels, like that. It is a very huge one. So to make you understand, I have taken only 5 by 5 pixel image. So now stride is defined as 1. So you can see there is, like initially there is a red color matrix which is 3 by 3. That is extracted from our image, and A is that one. You can see a 3 by 3 matrix which is named as A there. Stride is 1. A step forward is taken here, 032241011, which is a matrix B. So with one step forward, I have extracted another matrix B. Like that, if you still proceed further, you will have 324410113 as another matrix C. Then after that one, it comes down by one step, 024101102, like that. So it takes one by one strides to complete the entire matrix. It scans the entire matrix, that is your image. So now what are these values? 1, 0, 3, 2, 4. Some digits are being there on the image in each pixel's place. This is known as picture value, pixel value. What do you mean by pixel value? Your pixel will have some color in it, some edge in it. So based on the type of or shade of your color, based on the shade of your, like a small line may be there in the first pixel. A blue color will be there, or a faded blue will be there, or dark blue will be there. Even in blue color, you have n number of shades, like 255 types of shades will be there. So each shade is given a weightage. So that value is given here in the place of pixels, like 1, 0, 3. If it is black or gray color, something like that. So every picture element is given with one weighted value for its picture element. So those are being now extracted with stride 1. Now we need to choose our kernel, that is filter, which is seen here in the yellow color. So that kernel is based on the application. You can choose Sobel kernels for edge detection, or a Canis kernel, something like that. Here a Sobel kernel is taken, which has the standard values 101, 2, -1, 1, 102. So now we are going to perform a dot matrix operation on A and K. So if you see A and K, so that is being shown in the arrow sigma of A multiplied by K. So every element, both are 3 by 3 matrices, every element is directly mapped. You can see a sample calculation on the screen for the first filter location. You are able to see, sir? Hello? Hello?
Yes, ma'am.
Madam.
You are able to see the sample calculation first filter location. So that is
Yes, ma'am.
direct multiplication, 1 into 1 plus 0 into 0. You can see element to element multiplication, and adding them, you got 9. So that is the value of your feature map in the first place of the pixel. But we have added a bias element of 2 there. Bias element is added in order to reduce the error at the end. What should be its value? Just for some kind of sample calculation, I have taken 2. But to arrive at the bias value also, we have a specialized procedure for that one. So for time being, we take bias value as 2, that is being added to 9, which is being calculated there. So total is added as 11 in the first place. Similarly, if you go to matrix B, which is multiplied by kernel, you can see there sigma of B into K, which you are given there on the screen, sample calculation for the second filter location, and the same is being given as 5, and same bias is being added, and it is placed as 7. Similarly, as I said, 3 in the horizontal striding operations, you will get 23. Again, coming down, the next 3 by 3 matrix, you will get 14. Similarly, 7, 12. Total 9 operations like A and K, B and K, C and K, D and K, like that 9 operations will be done. Adding bias to them, you are going to get the output matrix which is of size 3 by 3. So what did we do in the convolution example? From the input image of 5 by 5 pixel size, you have reduced that one into a feature map of 3 by 3 size, which has all the information about the picture elements. So the size is being reduced. What is the need for reducing the size? If you reduce the dimensionality, you are going to consume less computational time. So that is the example from the convolution layer. Then after getting the feature map, same feature map I have taken in this example also in the same thing. So what is a pooling layer? From the feature map of input, so you are going to take with one stride. So 11, 7, 14, 7 is the first one. Next move 7, 23, 7, 12. So like that come down 14, 7, 11, 7. So as I said earlier, we have discussed there will be two kinds of pooling operations. One is maximum pooling layer, another is mean pooling layer. So in the maximum pooling layer, you are going to select the maximum value from this one. From 11, 7, 14, 7, 2 by 2 matrix, you are going to take maximum value of 14. Similarly, from the mean pooling layer, mean value of that one is 9.8. So from the second matrix of 2 by 2, 7, 23, 7, 12, maximum value is 23, mean value is 12.3. Similarly, if you come down like 14, 7, 11, 12, maximum value is 14, which is being placed here, and the mean value is 11. The second one is 7, 12, 12, 11. Again, maximum value is 12 and the mean value is 10.5. So you got a 2 by 2 matrices from the pooling example. So after getting that one, you need to now, so you got the maximum pooling layer at the end. You can perform n number of filters and get your pooling layers. So now we need to flatten that one. This is a 2D one. Flatten that one to represent 1D because we need classification of data. So for that one, what we need to do, you need to represent your matrix of 2 by 2 into a vector form now. So that's why we have represented that into a vector form by writing in a column matrix. That is 14, 23, 14, 12. So this is the last stage, that is smoothing of softmax layer, what we call, in which we will be flattening the data into a 1D one, which is going to classify our data. So this is a small example of an image which is represented by only 5 by 5 pixels. Imagine if you take an image of 1092 by 1092 pixels. What is the size of the matrix? 1092 by 1092. Every matrix element is going to represent the weight of that color of the picture element in the 3D, because whenever you are representing, it is going to be 250 by 255 by 3. 3 is the depth of your image, that is represented in RGB, red, green, blue. So that need to be applied with all the kernels and then perform pooling operations, n number of pooling operations, so that you can reduce the size to 2 by 2 and then into a single vector which is going to represent a class of your image. Whether it is having a crack, you will be defining that, or a spalling, or a bolt, if it is tight or loose, something like that. Next, it is passed to fully connected layer, as I said. So it helps us to make final classification predictions. And then once it is done, one epoch is completed. Epoch is one complete pass of an image. Then we need to calculate the loss, measure how far the predicted output is matching with the actual one. So if the difference is much high, then you are going to now add some weights, add some bias element, calculate that using cross entropy or mean squared error, MSEs, or sometimes R square also. So absolute errors also. So based on that, again go back. So that this is what is known as backward propagation. Whatever we have done in a single pass or in a single epoch is forward pass. Now we are going backward propagation and then doing the entire process once again and then again calculating the cross entropy loss. So till the loss is minimized, we will be calculating for each epoch what is the accuracy. So this is how we will be doing this one. As I said, back propagation and optimization. So the application of this convolution neural network process, what we have learned till now, can be applied to any kind of image based problems like image classification. So this image classification is used for identifying handwritten digits, categorizing the images into different classes. If you take a road, it will be having cars, buses, two-wheelers, electric poles, trees, people, men, women, children. So many things will be there. You can classify. So whatever are the contents that are there in the image. The best example is our face recognition. If we are going to give your face recognition biodata in the airports or even in the institutes or offices, how it is going to recognize the data? Lots of facial images are being fed into that one. So for every face, it recognizes by dividing the given image into number of pixels, and each pixel has its own colors. Like for our faces, we'll be having different color of eyes, different eyebrows, eyelashes, nose. Every feature, every skeletal features of our face are being unique for a given individual face. It can identify the image the moment it is being given. It matches, try to get the object detection, what we call. Second one is that only. CNN for object detections. There are various other methods: object recognition, medical image analysis, autonomous vehicles, and in the health monitoring of structures. So there are various architectures of standard CNN models. We have AlexNet, VGGNet, GoogleNet, ResNet. In the present case, I'm going to take an example of ResNet for the structural damage detection. There are special CNN models also: MobileNet, SqueezeNet, and EfficientNet. Every CNN architecture has its own advantages and disadvantages and is also dependent on the use case or application what we are going to apply on. There are some more advanced CNN models like DenseNet, ExceptionNet, Wide ResNet. Even in ResNet, we have different layers, like number of layers: ResNet 18, ResNet 50, ResNet 100. Depending on number of deeper layers, they are being noted like that. The more are the number of layers, more computational time, more GPU capabilities it requires. So like this, lot of advanced CNN models are there. So this is in brief about the CNN architecture. Very basic example we have seen. So to implement that one for our real time or real life examples, we require computational resources. What sorts of computational resources? We can use different kinds of platforms like Python, Google Colab, TensorFlow, so many things, computer vision, CV, OpenCV. So like this, we will be utilizing lots of open resources which are available. So to use those things, we need to customize our algorithms. Lots of algorithms are available. Pre-trained models are available with Kaggle or some other kind of sources. You can adopt from there, customize as per your needs, and then you can perform your algorithm tasks. So today I'm going to deal briefly with the research what is going to happen at our laboratories, that is bolt loosening detection in steel connections using image-based CNN architecture. This is part of the funded project received from Serbsure. So that is autonomous tool development for bolt loosening detection in steel structures. So this is, as you can see from the figure, there will be lots of bolted joints, not only in bridges, even in buildings, chimneys, towers, transmission towers. So many things are there. Whenever all these structures are subjected to dynamic loads like wind or vehicle loads or earthquake loads, the bolts are tend to loose. Generally in civil engineering, we use friction grip bolts. Entire load is transferred 50% by the friction mechanism only. So, but whenever the bolts are loosened, as we discussed earlier, there will be manual inspection which is going to be done, and the preload is again checked by means of torque wrenches, and then again they'll be tightened. To avoid this sort of manual inspection, so we need to now take the images through the drones And then we can visualize how many bolts are there in a particular joint, what is the size of the bolt, whether it is tight or loosened. If it is loosened, by what degree it has loosened, so that you can perform the structural integrity calculation for that particular joint, which are going to threaten the joint integrity, so that immediate manual intervention can be done to tighten the bolts in that particular joint. So that is the entire purpose of the research for this particular example. So you can see this entire process of the bolt loosening detection here. So the video acquisition through the drones. Drones will be different for different purposes. This is an inspection drone which will be having some optical zoom cameras. Wherever there is inaccessible points for manual intervention, these drones can be flew there. So we can collect the videos or either photographs also from there. N number of videos or photographs, you can extract images from that one. Then these images need to be processed. You need to segment the each and every bolt from the bolted joint. Segment the bolt, label it through different platforms, label each and every bolt, what is its diameter, label 1, label 2, something like that. Then apply that entire imagery data. If you have 3000 images of bolts, different bolts, then give that as an input for your deep learning CNN model. Now each image is now represented as a matrix of pixels. The procedure what we have just now seen is applied there with n number of pooling layers, introducing our RELU, rectified linear unit, by introducing non-linearity into that model, and then reducing the feature maps, extracting the feature maps, reducing their sizes, again performing this forward propagation, and then calculate what is the loss at the end, then backward propagation. So like that, perform n number of passes which are known as echoes, and then reduce the loss function, cross entropy loss, till you achieve minimal loss in the predicted and actual values. So later on at the end, so they are going to be classified whether the bolt is tight or loosened. Further, if we want to see the degree of looseness or quantify what is the looseness, then you can predefine how much pre-torque is being released to say that bolt is loosened by 0.4 is the degree of looseness, 0.67, something like that. So that's how even you can classify. Now we have seen only a binary classification in this presentation, whether tight or loose. So for that one, we now need to prepare a data set. So data set should be robust, because as I said earlier, so for the end prediction is going to depend on quality of your input data. Here the data is in the form of images. So you need to collect lot of images, n number of images with good quality, that is with good resolution. So you cannot take with a mobile phone and then send it through WhatsApp. It reduces the resolution. If you want to take through a camera or DSLR camera or through a drone image, then you need to preserve the originality of the image in terms of resolution and then store the data. So from the fabricated models in the laboratory with the different sizes of the bolts, diameters, different materials, we have collected the images through a mobile camera only, that is iPhone camera, which has good clarity. So the parameters of the image is, the size is 5712 by 4284 pixels. So you can imagine this is the size of your image. We have seen the operations only on the 5 by 5 matrix of pixels. So this is the matrix what we are going to deal with. Now imagine the computational requirements for this one. So what is the vertical resolution? 72 dpi dots per inch. So horizontal resolution and the bit depth and the aperture focal depth. So everything are need to be set. What are the parameters? Because your predictions are going to depend on the parameters what you are choosing. So the fabricated model, for example, I have shown only one kind of fabricated model. So it is a lap joint with the M20 bolts, and bolt hole diameter is 22 mm. length of the plate is 300, thickness is 8 mm, depth of the plate is, that is width of the plate is 100 mm, pitch distance between the bolts is 50 mm, gauge distance is again 50 mm, fabricated this one with a lap joint. A total of 661 images were captured in the laboratory with different light intensities, different distances, like we have taken from 1 meter, 2 meter, because the quality of your image is going to depend on various parameters, the shooting distances, the shooting angles, the light intensities, everything. If you have dull light intensity, the predictions may vary. That also influence we need to study. So we have taken images for different illumination intensities like 140 lux, 5100 lux, 38,200 lux or 77,400 lux from the different lighting conditions, keeping them outside in the sunlight, in the laboratory lighting conditions, on a cloudy day, at different timings of the day. So using a lux meter, we have measured the intensity, light intensity, and we have captured the images. And then after capturing the image, now I need to give only one bolt, but my joint is consisting of 4 bolts, sometimes in some models 6 bolts, in some models 19 bolts, something like that. So now I need to extract every bolt from my image of multiple bolts. So for that one, we are going to apply one more deep learning CNN algorithm, mask or CNN. Every bolt will be masked and it is taken out from that multiple bolt imagery. So isolating from the background, which helps focusing on the bolts by outlining their exact location, preparing the image for accurate classification. So once masking is done, it is easy for the ResNet, that is another CNN model, to handle the images with cluttered or noisy background, focusing only on the bolt. So for that one, we have done segmentation part. First part is capturing and then segmenting the data, segmenting each and every bolt from its parent bolted joint, and then cleaning that image from the noisy data. So lots of steps into the algorithm we need to give as the input, and then improving the model's ability to distinguish between tight and loose bolts. So now we need to send our data for the classification task. Take all the images out of the dataset folder, label accordingly. So how to label them? There are various platforms which are available to label the data. So we have utilized one such kind of platform to make sure the data is balanced. Now the images are in each category. We have collected tight bolts, we have collected loose bolts. So maybe we have induced, we have simulated from a given joint, loosened some bolts by some kind of preload relaxation, and we have taken 2 rotations loose, 4 rotations loose, half a rotation loose, completely tight. How can we ensure a bolt is tight? We have calculated the preload based on the diameter of the bolt, based on the material of the bolt, based on the friction quotient between the parent and bolt material. We have calculated the preload, applied that one with the torque wrench, ensured that it is in tight condition. If we release the torque, it will be loosened. By how much? By number of rotations. So like that, we have simulated the damage in terms of loosening the bolts. So now the pixel values are normalized by dividing by 255. Suppose for individual bolt, you have got 4026 by 4026. Now dividing by 255, we have normalized the pixel values. So this is going to help our model to converge faster and perform better. So like this, we have done for the entire bolt data. That is, in this case, only 661 images. That is not sufficient. That is a very small data set. Further, we need to augment that data, enhance the data size for better predictions. How to augment the data? We have applied a lot of augmentation techniques like flipping, scaling, rotation, so many things. So from the same bolt, we have scaled that one, we have rotated that one. So that our training data will possess diverse data sets. So randomly shuffle the data sets to prevent any order related biases during training, ensuring more generalized model. Now the data is split. Next step is splitting of the data. Why we need to split the data? To train the data. So take out 70% of the data set. If you have 1,000 images in your data set, individual bolts, take out 700 for training and 150 for validation, 150 for testing. So keep them in different folders. So training set is the largest portion of the data so that the model learns different patterns from different instances. The validation set evaluates the model's ability to generate from the unseen data. So training data will not be there in the validation. It is completely different, but it also has tight and loose conditions. So now after learning from the training data set, now the model is trying to learn which is loose, which is tight from the validation data. The exact values are known to us. The model is going to predict something, whether it is able to predict correctly with the existing label or not. That's where we need to calculate the loss of prediction. So now by fine tuning some kind of parameters, hyperparameters, we can prevent overfitting during the training. What do you mean by overfitting? Sometimes your actual data is going to learn in each pass differently. Your predicted data is going to behave in a different fashion. So that zigzagging is known as overfitting, which need to be avoided by generalization. So ResNet is used in the present computer vision task, that is image classification. In our case, it is binary classification of loose or tight of the bolt status. ResNet 50 is used here, which consists of 50 deeper layers, which includes convolution layers, normalization layers, activation layers, pooling layers, and the last one is softmax, that is fully connected layer for final output classification. So the key component of ResNet model is residual block, which allows the network to learn residual functions. That means it is going to reduce the vanishing gradient from the input layer. This is the architecture. You can see the input image of different bolts. I have shown here only 6 bolts. Like that, you may have 1,000 bolts, which has 0 padding, and then it is given as input to the convolution layer. Every bolt is fed into this one, only one bolt image at a time. So for this one, whatever we have discussed, different pooling layers in different stages will be applied to that one on the feature maps extracted, and it reduces the spatial dimensionality. So at the end, it will be having 2D, and then finally fully convoluted layer is going to have a vector representation for the classification of the data output. So this is the convolution block and identity block of residual network in the ResNet. That's why it is called as ResNet, residual network. So this is the identity block and convolution block. It is same as the identity block, but in this one, convolution layer is the shortcut path just to change the dimensions. So these are the training parameters which are adopted. Number of classes, sorry, this is by mistake 7. It is only 2. Optimizer adopted is Adam optimizer. There are various optimizers which are available. So Adam is the one which is more suitable for image kind of data predictions. The learning rate is 0.001. We can fine tune this learning rate also. You can start with 0.1, increase that one for minimizing the losses. The batch size also can be increased, like 32 is the least one. At a time, 32 images, that is the batch size. So if your data is consisting of, let us say 256 images are there, then there will be how many batches? 256 divided by 32 will be there. So like 8 batches will be there. 8 batches will be fed into this one as one pass. That is known as one epoch. So like that, the batch size can be increased to 64, 128 or 256 maximum. So the training hardware required is that NVIDIA GPU with RTX 6000 with 2 TB GPU, and weight decay is 0.0001. So these parameters can be fine-tuned for better predictions, that is to minimize the losses. Then after doing this, we need to evaluate the metrics. As I said, If your model is having only 0.9 as the accuracy, what is happening to that 0.1? It is not always necessary that all the predictions are going to be true. There will be true positives, true negatives, false positives, and false negatives. So there are 4 metrics which can be defined, that is accuracy, precision, recall, and F1 score. How they are calculated? Based on our confusion matrix. Confusion matrix is the one in every epoch. A matrix is prepared. How many true positives are there? How many true negatives are there? How many false positives and false negatives are there, which are represented by the color code. The darker one is the false positive, true positives. So like that, accuracy is calculated from the confusion matrix, true positives plus true negatives by total predicted instances. Similarly, the precision. The recall is model sensitivity to actual positive cases. Sometimes the bolt will be loosened. It is going to predict as loosened only. That is actual positive. Even if it is loosened, sometimes there will be false positive. Even if it is loosened, it will be predicted as tight. So all such kind of instances are represented by means of numbers in the confusion matrix, and these evaluation metrics are calculated. F1 score is the harmonic mean of precision and recall. So initially, imagery data set is created. Model training accuracy is improved with the number of epochs. Generally, we give the number of epochs as 100 or 200, something like that. Once the convergence values for the accuracy is achieved, the model will stop training its algorithm data set. So after 50 epochs in this case, model achieved optimal prediction accuracy of 0.9748 using ResNet 50 architecture, which is a very good accuracy, prediction accuracy. So it has stopped after 50 epochs, even we have given as 100 epochs. So here you can see for 10 epochs, the test accuracy is this. It tries to learn after every 10 epochs. When it reached 100 epochs, the required accuracy, test accuracy is achieved. So training accuracy is different, test accuracy is different. It learns different parameters from the training and tries to validate. You can see the test accuracy versus epochs here. So as I said, lighting, impact of lighting condition on damage prediction, different lighting intensities are, images are captured from different lighting intensities as mentioned. So it is understood that it performed poorly under low lighting conditions because the low lighting condition images are less effective to extract the feature map from the image. So that indicates model performance is significantly influenced by the lighting intensity. If you take in the daylight, if you take on a cloudy day, if you take on a sunny day, it is going to impact your damage predictions. So you can see few of the data sets under different lighting conditions. You can see the difference in the images here. Low lighting conditions, they are darker. Better lux intensities, you have more clear images like this. So under 140 lux, least lighting conditions, you can see orange color indicating validation loss, and blue color line is indicating training losses. So model is improving. First one is training loss, second one is accuracy, third one is precision, fourth one is recall and F1 scores. So here you can see what is the difference between the training and validation losses. The difference should be very low. Both the orange color and blue color figures trend is seen to be similar, but the gap between them is much high. So learning rate shifts optimizer instability. You can see this is very unstable model. So the positive predictions are not being made. If you see other lux lighting condition, that is 5100 lighting condition. So you can see here the difference between the previous case and this case. The patterns of your orange and blue colors are almost the same, and the distance between them is also very small. So, but however, if you see the recall and F1 scores, so the more zigzag patterns are there. So that means the data is overfitting. It is showing overfitting. So, but the precision graph shows the predictions are steadily increasing. The number of epochs are more and more. The prediction is better way. For less number of epochs, the prediction percentages are very, very less accurate. But gradual improvement is there in this one. So if you increase the lighting conditions here, you can see the gap between the yellow, orange line and the blue line. The validation losses are being minimized. Even in the recall and FN scores also, they are very, very small, but there is little overfitting in the initial stages of your algorithm. The highest lighting conditions, 77,400. The model performance is better seen, which is showing very, very balanced performance. High precision is been demonstrated by this strong classification model. So like this, we can apply for different classifications, different problems. The study successfully demonstrated that deep learning techniques, specifically using resonance architecture, can accurately detect bolt loosening in steel joints based on the image data sets. The CNN-based ResNet model achieved very high accuracy, precision, recall, and FN score, highlighting its robustness and efficiency in predicting the bolted condition. Model demonstrated very high accuracy of 97.48%, reflecting strong capability to accurately classify the bolts. Model accuracy, precision, recall, and FN score were all marked enhanced by higher illumination intensities. This is what we have seen. And we have even applied just for this framework what we have developed. We have just given an input from the random bolt image from the real world situation, like even anchor bolt from a gusseted base of a communication tower which is fixed to the concrete pedestal. Take that image and we gave that one to the framework. It has predicted very, very accurately whether it is tight or loose. And though I have not presented here the degree of looseness also, it has predicted very well. So the test result showed that prediction accuracy could be affected depending on different lighting conditions, also shooting distances and shooting angles also, which I have not presented here. So these are few of my references. Thank you very much. Any queries, please? You can feel free to ask.
Ma'am, I have a doubt because some that these screws they are like even though they get jammed, but they are more have much holding capacity than I mean, it seems like they are getting loosening, but even they are jammed. It's not easy to get them pull away from the bridge. So how can we say that those nuts are getting loosened based on this gap, or only based on image?
Yes, ma'am. I understood your question. Like sometimes the bolts will get corroded, maybe age-old kind of bolts, but it is very difficult to pull them. But over a period of time, because majority of the bolts are subjected to dynamic loads, our major concern is whenever there are dynamic loads like vehicle passage or wind loads or something like that, it may get loosened, but there will be a structural integrity calculations need to be done for that joint. If your bolted joint is going to consist of 20 bolts, few bolts may be rusted, few bolts may not have that loosening exposure also, but still they are in the condition very difficult to pull out. So only loosening part is not the only kind of damage metrics to say that kind of bolted connection is more prone to damage. But there are various other parameters, like as you said, maybe bolt is corroded. Sometimes bolts may split also because of more rigid torque applied onto that one. The splitting of the parent metal also is going to happen. So only loosening part is not based on the screw height which is going to be exposed. There are various other parameters. This is only a study to just demonstrate image based detection also is very powerful tool in assessing the damage in the bolted connections, ma'am. Hopefully, I answered your question.
Yes, ma'am. Thank you. Ma'am, has like when we take a image from a drone of these screws, it also, I mean, if we see to the different sides, we see to the different distances mostly. I mean, if we zoom in, because as we can see in like mobiles, if we just keep on some plain platform, and if we take a picture, we don't know what the dimensions are unless they have mentioned it. So likewise, even the bolt became corrupted somewhat if the drone took the image. We may see the distance because some part was missing, or there is no part missing because the angle may be different. So how then the accuracy, won't they get I mean, even the accuracy increases according to the machine learning, because there is no manual interaction. It may lead to it's under in a biased condition. I mean, it's a part of loosening condition. So how can we correct this type of biases?
Yes, ma'am. That's why I said your end output or predictions are going to be dependent on the quality of data set what you are going to take. So the data set, the predictions are going to be influenced by not only lighting conditions, as you said, shooting distances, from how far you are taking the video or image, and shooting angles. If it is from the front view, you will not be able to exactly see how much is the loosening. That's why the pixel matrix is going to be very, very important. Even if the bolt is slightly loosened, if you take from the 90 degrees image capturing, you will not be able to find out. So that's the reason why your initial data set should consist of lot of diversity in its image collection, lot of diversity in terms of lighting, in terms of shooting angle, in terms of temperature, in terms of distance. So lots of parameters are going to influence, ma'am. So sometimes you need to collect the data from the real world situation, from the laboratory model, from the internet sources, different, so that your model is going to learn from all these training data. As I said, 661 laboratory model images are not sufficient. So we started, I just presented a sample here. We just started with 5,000 data set, which is very much diversified. So you may have rusted bolts, you may have reduced diameter bolts, not only 20 mm bolts, you may have 6 mm bolts, you may have different grades of bolts, different types. So the training data should be well diversified so that the algorithm learns in a proper manner with greater accuracy. Though the training accuracy is 100% also, but the validation accuracy is going to matter for us. But using all these CNN architectures, the maximum accuracy what we can achieve is just between 0.9 to 0.93 or so. Because if we are able to achieve that, it is a great achievement, because in majority of the cases, what we are seeing is bridge inspection, for example, is a very costly affair, very, very costly affair. If you deploy sensors also, 100 sensors at different intervals, and the location is also need to be optimized with respect to more damage prone locations like plastic hinge formations or something like that. Even though you deploy a sensor network there, sensors are based on some kind of energy. Not all the sensors are going to be self-sufficient to draw the energy from sun or solar or something like that, or through Wi-Fi. It is a very, very costly affair. Sometimes if some of the sensors are not working also, we are not able to get the data from that particular location. So instead of all these sorts of things, computer vision, that is image based deep learning methods, are going to give a certain kind of predictions from a old kind of civil infrastructure like bridges or chimneys or tall structures, such kind of things. through which we can integrate through our manual calculations or any kind of using any software. Suppose in a 20 bolted joint, if 4 bolts are loosened by 90%, if 2 bolts are not loosened, if few other bolts are loosened by 40%, how much it is going to affect the integrity of that joint, that we can do structural calculations and evaluate immediately, the action can be taken. That sort of things are possible using this kind of deep learning algorithms. That's the entire motto behind CNN architecture.
Thank you, ma'am. Ma'am, is there any possibility to know whether it is overfitted, correctly fitted, or is it, I mean, if some people misses, before fixing the bolt, we keep that, oka hole laga undedi pettam kada madam. So, is there any way to recognize the differences of these things like it got overfitted? Because if you overfit also, it bends more
Overfit leads to more rigidity in the joint, madam. It is going to damage the parent element. So that's why we need to calculate generally in the manual, in the field, what they do is they calculate the preload. Generally, we will be seeing that in automotives, preload for the bolt, and they're using torque wrench only. They are going to digital torque wrenches also will be there. There will be digital display. How much is the preload to be applied? Only they turn the bolt to that extent, they'll stop it. If they are turning it more than what is required torque there, then it becomes more rigid, which is also going to cause the damage in the initial stages.
Yes, ma'am, you are right. I mean, through if I take an image, can I just by image can I identify that it's got overfitted and it's not overfitted?
That also we can take up as one of the
mistake,
research problem,
what
ma'am.
I
We
have
can see.
done with unknowingly. Because
Yeah, we can take up
will
that
be
as a research problem, and we can do. That is also we have done, ma'am.
Okay, thank you.
And patent also we have published. Any other queries, sir? If no other queries, I would take this opportunity to thank the organizers of Department of Civil Engineering, Bapatla Engineering College, sir. Thank you very much for giving me this opportunity. Thank you, sir.
Madam, one doubt is in there in the chat box.
Yes, sir. I'm saying.
Chat box, one of the person has asked regarding this.
I'm not seeing any doubt, sir. Message has been deleted, Anandi.
No, ma'am. Could you go down? That chat.
No, sir. I'm looking in the chat only.
From the faculty, Dr.
Ma'am, can I say, they asked like, does max pooling reduce overfitting in control neural networks or RNN? Which technique is better for looking out this overfitting?
To reduce overfitting, what we generally do is we apply some hybrid model at the end, madam, for the CNN models like LSTM models, like large, short training models. We apply early stopping techniques so that it is going to converge. So there are various other techniques where you can fine tune your model. It is not as simple as we have discussed in this session. There are lots of fine tuning parameters which can be done by applying so many parameters into our algorithm. Sir, I am not able to see any other query, sir.
Only one, man.
Sir, if possible, can you read that one? I am not able to see the query.
The thing which madam has asked, has max pooling reduce overfitting in CNN or RNN? Which technique is better for overfitting? The same question. Only one question has been asked.
So as I said now, sir, CNN along with fine tuning with early stoppings, to avoid overfitting, generally what we do is apply some early stopping techniques, sir.
Okay, ma'am. No more questions.
Okay, sir. Thank you.
Thank you, ma'am.
Okay, ma'am. Thank you. It was a nice presentation. We personally, I really enjoyed it, ma'am. Because I am one of my branch is remote sensing. So,
Okay.
so really liked it, ma'am. So,
Thank you,
you,
sir. If any queries are there in, for the
no,
participants,
no,
my
ma'am.
mail ID is there. It is being displayed in the very first slide. Thank you, sir. You are always welcome to collaborate in any of the future research also. I'm available, sir. Thank you. Hopefully I can leave, sir.
Yes, ma'am.
Thank you.
Thank you, Madam Mallika, madam.
Feedback link is been provided in the chat box. Please kindly.
Hello, sir. Hello, sir.
Sir, please.
Can you please send again, sir? It is not showing.
It is also available in the WhatsApp group, sir.
Okay, sir. Thank you.